All right, 8.1 exponential models. So in this one, we're going to be graphing some exponentials. We're going to be graphing some exponentials, and we're going to be solving a few applied problems. So starting off, what is an exponential function? So an exponential function, what is it? It's a function of the general form. We'll say general. The general form is y equals ab to the x, where the x is in the exponent. In this, a is not equal to 0, b is bigger than 1, and b is not equal to 1. The domain of this function is, how do I write that? The domain is x is in the reals. There's no root, there's no denominator, so it's just the all reals. Now, whenever we start graphing this, you've probably seen an exponential curve, especially with COVID going around. We have this point here that's at 0, a. Maybe I can write that a little bit better. 0, a. So a tells us how high up our y-intercept is going to be, right? This is our y-axis. And then it's normally going to look something like, maybe I can do that just a little bit better. Something like that. That is really bad, but oh well. Yeah, that's pretty decent. It starts off very flat, and then it goes almost vertical. So A, like I said, shows how high up or down. B shows, or B, we'll say changes, or yeah, changes how much it is stretched or shrunk, right? We thought about, we talked about that with parabolas and things like that. It's not, it's kind of the same. It's a little bit different, but it's mostly the same. Stretch. Talking more about B, whenever B is greater than 1, it is a growth factor. And that's supposed to be a little arrow there. A growth factor has B of bigger than 1, and whenever B is less than 1, it's a decay factor. This here shows growth. If it were decay, it would do something a little bit more along the lines of something like that. It would start tall and it would end shallow. All right, more vocabulary. An asymptote. Asymptote might be a new word for you. An asymptote is a line that continually approaches a graph but never touches it. For asymptotes, what we're going to be dealing with is we're going to be dealing with horizontal asymptotes, right? Left to right. In our graphs up here, you could think about there's a horizontal asymptote right here. And I know that we haven't graphed them a whole lot, but this graph here will never touch that. It'll keep getting smaller and smaller as we go that way, but it'll never actually touch the x-axis there. So let's look at the let's look at another one here, or an example rather. So example number 1, does y equals 2 times 3/4 to the x model growth or decay? Does it model exponential growth or exponential decay? So the way that we decide that is we look back up here. It had said that whenever b is greater than 1, it's a growth factor. Whenever b is less than 1, it's a decay factor. So we care about this piece right here. 3/4 is less than 1, so it is decay. And let me go ahead and see if I can pull up the graph here, and we can just graph this and look at it. So this is y equals, and I probably need to write in the y equals 2 times 3/4 to the x. So that's what that looks like, right? It comes down. So the answer to that is decay. Next up, number 2. We're supposed to graph with a t-chart. And what we're going to graph is we're going to graph y equals 2 to the x. Now, just so that we know, just so that we can kind of think about it, normally the general form here is y equals a b to the x. So in this scenario, a is 1 and b is 2. Now for our xy chart, xy table, whatever we want to call it, let's start off at like -2. Say -2, -1, 0, 1, 2, 3. Now, if we were to just plain old plug this in and not try to make it look, not to try to get the correct well, how do I want to say that? Not simplify it all. We're not going to simplify it all. I'm going to plug into this 2 to the x. So if I plug in a -2, I'm going to have 2 to the -2. So that's a -1. So this will be 1 over 2 squared, which is 1 over 4. If I plug in a -1, it'll be 2 to the -1, which is 1 over 2. If I plug in a 0, it'll be 2 to the 0, which is 1. 2 to the 1, which is 2. 2 squared, which is 4. And 2 cubed, which is 8. So we should be able to see that pattern there. If we thought about this more, right here we had the -2 that we plugged in and we got a 1/4 out of that. If it was a -3, we'd have a 1/8, a 4, a 1/16, right? That fraction is going to continually get smaller as we get farther to the left of our graph, but it'll never hit the axis. And let's graph this, and maybe that'll help a little bit to be able to see that. So starting off -2, 1/4. So -2, 1/4 will be somewhere right in there. -1 is at 1/2. 0 is at 1. 1 is at 2. 2 is at 4. And 3 is at 8. 1, 2, 3, 4, 5, 6, 7, 8. So up there. Now if I were to draw that in, it would look something like that. Now, like I said, over here, on this tail end of it, it will keep that fraction that's representing the vertical, the y, will keep getting smaller, but it'll never actually hit the axis. Right? So we have an asymptote, a horizontal asymptote, at, what is that going to be? Y equals 0. Horizontal asymptote at y equals 0. All right, this has a growth factor. It has a growth factor of 2. That's another good thing to know. What else should we know? A equals 1. Well, that means that it crossed right there at 1. I think that's all that we need to know from this one. We'll move on and let's do another one. Example number 2. Again, we're going to graph. And this time we're going to do y equals 4 times 2 to the x. So in this scenario, A is going to be 4, B is going to be 2. This is very similar to the last problem. What was the last problem? Y equals 2 to the x. This one's y equals 4 times 2 to the x. So that 4 will change it up a little bit. Let's again look at an XY chart. This one I'm not going to do it quite as many as we did last time. Let's do like -1, 0, 1, and 2. Whenever I plug a -1 in there, it's going to be 4 times 2 to the -1. So that's going to be 4 over 2, which is 2. Whenever I plug in a 0 in that, it's going to be 4 times 2 to the 0. 2 to the 0 is 1, so this is just going to be 4. Whenever I plug in a 1, it'll be 4 times 2 to the 1. So that's 4 times 2, which is 8. Lastly, we have 4 and then 2 squared, which will give me a 16. Now, whenever we try to graph this, we'll have something like that. And so -1, 2. Maybe we'll say that each of these increases by 2. So this will be 0, 2, 4, 6, 8. So -1, 2, we'll have a point there. 0, 4, 1, 8. And I'm not even going to draw the 16 on there, but I think we can see how this is going to go. It's going to have some kind of very steep vertical like that. Just like that. I think that's all that we need from that one. We'll go on to the next one. Did I have a number 3? Oh, this one was a number 3. There we are. That's number 3, and now we're moving on to number 4. It's almost like I can't read my own handwriting. All right, we're going to write an exponential function for a graph that includes two, 2, and 3, 4. All right, so we are given 2 points that are on an exponential curve, and we need to find what is the standard form of that graph. Now, let's remember what standard form is. It is y equals ab to the x. So really what we're looking for is we're looking for a and we're looking for b. Once we know a and b, we can plug in and get our standard form there. So let's start off by making 2 equations, plugging in everything that we know, which is going to be the x's and the y's. So starting off with the point 2, 2, that's going to be 2 equals ab squared. And then with 3, 4, that's going to be 4 equals ab cubed. Now continuing on, that's all that we can do there, but we're going to have to find some other little method here. So this is the real secret to this, is we're going to have to solve for a. So solve this one for a, and we get a equals 2 over b squared. And the bottom one is a equals 4 over b cubed. Now we know that A equals A. That's kind of a nonsense thing to say. So that means that 2 over B squared is 4 over B cubed. Now if I were to multiply by B cubed on both sides, the B cubes on the right would cancel. The B squared and the B cubed would cancel to just be a plain old B. And we're going to have 2B equals 4. So from there we can say, well, B is 2. All right. Now we need to plug back in to get A. I'll plug into the, we'll plug into the top one. I think that'll be a little bit nicer. So A equals 2 over 2 squared. But we can cancel some 2's out. This will just be 1/2. So A is 1/2. Then finally, we need to write it as standard form. So Y equals 1/2 times 2 to the x. All right, let me see if I can get the next problem to show up for us. This one's really long. There we are. All right, this is going to be number 5. This will be very similar to some homework problems, so if you want to, you can pause the video and copy this down, or you can look at number 13 on the homework. So, the population of an endangered bird species has decreased at a rate of 0.75% per year. There are currently about 200,000 of these birds. Write a function that models the bird population. And then how many birds will there be in 100 years? So starting off, let's look at our standard form of the equation. Y equals AB to the x. Now, in our model, right now, what we're going to say is right now we're on the y-axis. So let's look at that. Let's go back up to the top here. Whenever we're on the y-axis here, we're at the point A, right? We're at 0A. So A should be easy for us to fill in here because A is going to be 200,000, right? Right now we're starting off at 200,000. So this we can plug in really quickly. This is going to be Y equals 200,000 B to the x. Now B is going to be our decay factor. Right? It's going to be how fast are we decreasing? How fast are we getting smaller? Now, this is where it's going to get a little bit confusing in my opinion. We have this, it's decreasing at a rate of 0.75. Now, for starters, we need to convert that 0.75 into a regular number. Now, think about this. 100% is equal to 1, right? So what we do there is we take a decimal and we move it 2 spots to the left. So 0.75, the decimal moves 2 spots to the left, and we're going to have 0.0075. All right? This is how much it decreases, but that's not our decay factor. Our decay factor is going to be 1 minus 0.0075, right? If we had a 1, that would mean that nothing changed. That's like 100%, everything stays the same, but we're decreasing by 0.75%, so we have to take away 0.75%, right? This is the taking away of 0.75%. Whenever we subtract that, we should get something like 0.9, what is that? 0.9 something. 0.9925. So to update my formula here, it's going to be y equals 200,000 times 0.9925 to the x. So this models that equation there, this equation here, It's part of our answer, and that models the number of birds. Now what we also need to do is we need to plug in 100 years. So I'm going to plug in 100 into my x, and I'll just type that in here if I'm able to. So I'll type in 200,000, that's 5 zeros, times 0.9925, and then exponent 100. And it spits out 94206.6, and it doesn't really make sense to have 0.6 of a bird, so we're going to round up. 94207 birds. So there we are. This is the way that all of your the word problems there, I think they're in the middle of the page on your homework. That's how they will work. Number 6. What is the growth or decay factor? And we're going to have part A, which is plus 22%. So that would be like, if that was written in words, it would say an increase of 22%. And then number B, or part B, will be a decrease of 16%. So what do these mean? Right? In our word problem, it was written as a decreasing at a rate of 0.75%. So that's what the negative 16%. I can just kind of simplify that. So if you were given a word problem that had these words in it, what would we convert that to? Right? Well, an increase of 22%, let's start off by converting that to a regular number. So 22%, the decimal's right there, and we're going to move the decimal 2 spots to the left. So this will be 0.22. It's an increase, so I'm going to say 1 plus that. So it'll be 1.22, and this is a growth factor. Now for the negative 16%. I'll take my decimal and I move 2 spots to the left. This will be negative 0.16. And we're not percent anymore. So this will be 1 minus, because it's a decrease. So what is that? If I type that in, I say 1 minus 0.16, and that gives me 0.84. This would be decay. All right. Hopefully that helps with some of the word problems. Let's look at number 7. We're going to say find the amount of increase or decrease that the function models. Find the amount of increase or decrease the function models. In this one, again, I'm going to do 2 of them. Part A will say y equals 3, 0.5 to the x, and B will be y equals 20, 1.4 to the x. So what we're going to be doing here is we're going to be grabbing, the only thing we care about is the 0.5 and the 1.4. And we're going to be doing what we did in number 6, only backwards, right? We're wanting to find our growth or decay factor. Right, excuse me. We're wanting to find the increase or decrease as a percent. Right? We're given the growth or decay factor. So in A, our decay factor is 0.5. Right? How could we get that to 1? Right? How could we get that to 1? Well, that one should be pretty easy. It's going to be 0.5. Right? You just take 1 minus 0.5 to get the leftover 0.5. And then to turn that into a percent, move it 2 spots to the right, and I get 50%. Now, is this an increase or a decrease? this is going to be a decrease, so a negative out front. A decrease of 50%, right? Because it's 0.5. Now, if this was a 1.5, it would be an increase of 50%. Let's look at part B. Here we have 1.4. Well, we know that it's going to be an increase because that's bigger than 1. Right? So if we took, how did I word it? Last time I said 1 minus 0.5. We just want to find how far away from 1 is this. So this is going to be 0.4 away from 1. This is going to be like positive 0.4. And then we need to turn that into what do I need? It's a decimal right now. We need it to be in a percent. I'm going to move my decimal 2 spots. This is going to be positive 40%. All right, hopefully that helps out a little bit. And let's look at the last problem here, number 8. Number 8. And I think this is just a neat problem. A car decreases in value by 20% each year. Right, so we have some car, the car decreases by 20% each year. And this isn't too far off by how much cars actually do decrease every year. I know that whenever I was in driver's ed, I was told something along the lines of, whenever you drive off the lot with a new car, you lose 40% of the value of the car. And I was like, well, that's kind of true. So a car decreases by a value of 20% each year. The car is 5 years old and worth $11,468.50. What was the original value? And we're going to round to nearest $1. All right, this 20% is going to be a bit of an over-exaggeration, but it's a good way to see it anyway. So we're going to use our formula y equals ab to the x, and we're going to try to plug in everything that we know. We know that right now it's $11,468.50. That's going to be our y, $11,468.50. A is our original value, so we're going to be looking for A. B represents how much does it decrease every year. So in our head, let's look at this 20%. 20% as a decimal is 0.2. So it decreases by 0.2, so that means that it's 80% of what it originally was, right? 1 minus 0.2 is 0.8. And it's been 5 years. So solving for A, I'm going to divide both sides by 0.8 to the 5th, and I'll have A equals 11468.5 over 0.8 to the 5th. Now let's see how we can type this in. 11468.5 divided by 0.8 to the 5th. A. So what we get is A equals 34999, and we're supposed to round to the nearest dollar, so I'll just leave it at that. So $34,999. That was the original retail value of it. So like I said, that's a little bit of an exaggeration of cars, but it shows this value very well, or shows this how this can be used. So let me know if you have any questions, and good luck on the homework.